It is time to look at a special case of the inclined, which has friction on the surface. Welcome to my advanced physics class, where we discuss modern physics and classical physics. Kindly subscribe, click on the notification bell, comment, share, like my videos. So we have a frictionless pulley with a string, and then you have small mass, larger mass. There's a tension in the string which are equal in magnitude. We have mg and we have capital mg cos theta. This capital M. For the whole of this mass is capital M. This angle is equal to that angle. I've already explained that. Now, let's consider the case when this mass is about to move. It is just about to move downward. See? Now, when it is about to move, that means the sum of all forces in there, up and down, the inclined will be 0. And then the sum of vertical forces would also be 0. So mg sine theta minus the maximum friction minus the tension will be equal to 0. But we know F max. Then mg sine theta minus mu static times capital mg cos theta, where mg cos theta is the normal reaction, minus t is equal to 0. This is this direction is up down the inclined direction. Then we also write the equation that t minus mg will be equal to 0. That is the vertical direction. So t will be equal to mg. For that matter, we know t. So mg sine theta minus mu s times mg cosine of theta minus small mg is equal to 0. So this is an equation that satisfies the dynamics that this object is just about to move downward. So with this, you can calculate the critical angle at which it is just about to move downward. And then again, if you know that critical angle, you'll be able to calculate for the static friction. Okay. So downward motion, let's consider the downward motion of the whole system. So when the whole thing is set to move downwards, then mg sine theta, that is this force, now minus the frictional force. When it is moving, is the coefficient of kinetic friction, capital mg cosine of theta, then minus the tension will be equal to capital M times the acceleration in the up and down the inclined direction. That's the first equation. For the second, you have t minus mg will be equal to max. That is equation 2. So with this, we can manipulate and get ax, and manipulate and get t. If you want to get ax, just add the two equations. That is, this quantity plus this would give us mg sine of theta minus mu k capital Mg cosine of theta. This and that will add up to 0. We have minus small mg is equal to capital M ax plus small m ax. Then ax would give you mg sine of theta minus mu k capital Mg cosine of theta minus small mg divided by capital M plus small m. That will be ax. And if you want the tension in the string when it moves downwards, you can divide this equation by that. And for that, ax will cancel and you make t the subject. Okay. And this case will be similar to the case when there was no friction on the incline. Okay. So let's solve for the tension. Let's do that too. So for the tension, dividing the two equations, you have capital Mg sine theta minus mu k capital Mg cosine of theta, then minus t divided by the whole of this t minus mg would be equal to this divided by that. You have capital M over small m. You just have to multiply this quantity by small m, this quantity by capital M, then you make t the subject, and you're cool to go with your tension. Now let's read the physics into this equation. See, let's try one case when theta is 90 degrees, that the whole system is standing upright. For theta is equal to 90, the friction case will be 0, and sine theta will be 1. So that will be capital Mg minus small mg divided by m plus m. So then you're going to have capital M minus small m divided by capital M plus small m, and then divided by times g. So this is equal to 0, this is equal to 1. And for the case when the system is standing upright and the two masses are equal, then you would have the acceleration to be 0. The whole thing will be in equilibrium. It will look like this case. So the whole thing will be like so. And you would have this to be mg and that to be mg. The system will neither move in the leftward direction or the rightward direction. So that is the case when theta is 90 degrees. And for theta is equal to 90 degrees, let's just say capital M is infinite as compared to small m. So small m goes to 0. When small m goes to 0, the acceleration of the system would be g. Because this will be capital M over capital M. It will simply be g. So the whole thing will accelerate downward with the force due to gravity. Give it acceleration due to gravity. So this equation is right. And you can manipulate this and get the tension out of it. Okay. I'm very much interested in the tension. So let's complete this equation. If we do that, we have capital M times small m g sine of theta minus mu k capital M times small m times g cosine of theta minus small m t. That will be equal to capital M times t minus capital M small m g. I'm making grouping like terms, we have capital M small mg sine of theta minus capital M small mg mu k cosine of theta minus so plus capital M small mg, that will be equal to capital M capital T plus small m capital T. We just group like terms over here, and by so doing we can factorize. So capital M small mg out. For that matter, we have capital M small mg into bracket, we have sine theta minus mu k cosine of theta plus 1 divided by, if you factorize t out, you have capital M plus small m. That will be equal to the tension. So the tensional force in the string will then be equal to capital M small m times g. Then we have sine theta minus mu k cos theta plus 1, all divided by capital M plus small m. So once again, when theta is 90 degrees, this will be 0. This would be 1. 1 plus 1 will be 2. So that will be 2 times capital M. We are considering a case when theta is 90 degrees. G divided by capital M plus small m. That will be equal to the tension in the string when, the system is 90 degrees. And for 90 degrees, when these two masses are equal, then you have m squared divided by 2m. So then you have 1m cancelling the other m and 2 cancelling 2. You simply have mg. The tension will be mg when the two masses are equal. Then when one of them is infinite, let's just say this capital M is infinite, the case where this goes to 0, then the tension will be 0. The whole thing will accelerate and give it a tension of 0. The string will not be taut. So this case is also correct. That's a beautiful case. Okay. So given this inclined system with friction and the system accelerates downwards, it will give it an acceleration, this quantity. And the tension in the string would be this quantity. Okay. For the case where there is no friction, and this case goes to 0, then this case also goes to 0. Okay. Let's look at the last two problems of this episode. We are looking at a system where a road is banked. There's no friction on the road, but it is banked. And still, drivers can negotiate curves. Not only drivers, every vehicular user can negotiate a curve. Let's see. So before we look at the banking of roads, now let's say this is a runabout and there is a driver who is negotiating this runabout, a circular trajectory. Now, how is he able to negotiate this curve? That means there should be a force that gives it a centripetal acceleration, mv squared over r. And that is going to be provided by friction. Without friction, the whole system will slide away. It will skid. We call it skidding. So the maximum friction that the driver can apply, or the car can apply with the road, is mu s times the normal reaction force, okay, where n is equal to mg. Okay. So then mu s times mg is equal to the centripetal acceleration of force, which will be mv squared over r. See, now m cancels out, so we have v squared is equal to mu s times rg. So for a car to be able to negotiate this curve, a roundabout, this equation should be satisfied. That at every point on the circumference, the tangential speed square should be equal to the kinetic coefficient of friction, the coefficient of static friction times the radius of the circle times g. So v square is equal to mu s rg. So for a higher speed, there should be more friction. So for a constant friction, if you want to negotiate a curve of constant radius with a constant g, if you want to increase the speed, then you need more friction. But then you cannot get more friction. So what you have to do is, if your speed will have to increase, then you would have to negotiate the curve at a bigger radius. Okay? So if this is a runabout and with a constant frictional force, constant g, you want to speed up to negotiate the curve, then you have to negotiate the curve at a bigger radius. Other than that, you skid away. Or better still, you need bigger friction, which you cannot provide. You need more money to do that. Okay. But then, because of physics, we're able to beat the system. This is how we beat the system. Instead of you making a flat road, you bank it. You bank it at an angle theta. Just bank the road. So now this is the car. The car is part of a bigger curve that goes inside the blackboard and comes out. So it is a road that goes into the blackboard that way. Just have to imagine that. So then this is mg of the car. Okay. This is a normal reaction force N. Okay. Now this road is part of a circle. See, the road goes as a circle. Okay. So then if this is the center of the circle, you need kind of a component of the normal reaction towards the center of the circle. And you need a component which is also parallel to mg. Okay. And the fact of the matter is, if the whole incline is lying flat on the ground, mg will still be vertical. Now normal reaction will be vertical too. You see? So as you start inclining the whole system, then this angle will also be theta. So when the whole thing is flat, normal reaction, so for the flat system, this is mg and this is n. But when you start inclining it, and this n will tilt by the same angle this one tilts upwards. So theta is equal to the theta here, and then this is n cosine of theta, and this is n sine of theta towards the center of that circle that the banked road is part of. Okay. So this direction is n sine of theta, which is the same as this one. See, so the equations that we have to write is mg is equal to n cosine of theta, and then we have n sine theta, which gives the car its centripetal force, mv squared over r. See? And when we divide this equation by that, so we are dividing this by that, we have n sine theta divided by n cos theta, we have tangent of theta. Then we have mv squared over r divided by mg, we have v squared over rg. So v squared will be equal to rg, the tangent of theta. There is no friction on this road, but yet you can negotiate the curve satisfying this equation, where at every point in time your tangential speed is equal to the radius of that circle, or that banked road, times g times the tangent of theta. So as your speed increases at a constant angle and a constant g, you have to negotiate the curve at a bigger radii or at a bigger radius. So your car has to negotiate the curve much higher on the plane. As you come down, the circle reduces radius. You would have to negotiate the curve at a lesser speed. So as V increases, R has to increase. Or better still, if you want more speed for your banked road, then you bank it at a higher theta, at a higher angle. And drivers can negotiate the curve at very high speeds. But whichever the case, it has to satisfy kind of this equation. In order to prevent skidding. So skidding is a case when you negotiate a curve at a speed very high, but at a small radius and at a very small angle. So your negotiating of the curve doesn't satisfy this equation. That's why we say you skid, and you would have to move in a linear direction away from the road. Okay. Thank you for staying with me. We have analyzed friction on inclined planes. We've seen some uses of that. Even on a frictionless road, if you bank the system, you can still negotiate the curve, provided this equation is satisfied. We are now moving into a more beautiful stuff. We call this the law of conservation of energy. A law that the entire physics rests. It has been able to defy all odds, even the quantum revolution and the general theories and special theories of relativity. Those revolutions couldn't kill the law of conservation of energy. That will be our next episode. Stay tuned. Kindly subscribe, share, click on the notification bell, and like my videos.